So what we're going to do is some trigonometry of right triangles. I'm going to do a couple different examples, but the first one I like to do is these two special triangles. So first of all, what is trigonometry of right triangles? If you have a right triangle, usually we label these as X and Y and Z, or A and B and C. What we're saying is if you have an acute angle in a right triangle, so a right triangle means one of them is 90 degrees, the hypotenuse is always the largest side standing opposite to 90 degrees, and then we have two legs. Once we fix one of the acute angles, this one is called the adjacent side to the angle, and this is the opposite side to the angle, and then we have SOHCAHTOA, or whatever you want to use to express these things. But basically what we're going to use is a bunch of trigonometric ratios as defining cosine of theta. If we relabel these as hypotenuse and adjacent and opposite, what we're going to get is cosine of that is defined as adjacent over hypotenuse. Sine theta is defined as opposite over hypotenuse. And tangent of theta is defined as, well, it can be sine over cosine also, but in its definition is opposite over adjacent. So I know, exciting. I'm excited too. I know, super exciting. You want to do some? She likes trigonometry. Once we have those three trigonometric ratios in mind, sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tangent is opposite over adjacent. Once we have these trigonometric ratios and we don't stumble as we try to explain them, then what we want to do is build nice unit circle values or calculatable values for sine and cosine for certain angles, and then we use them a lot in other calculations in mathematics. So the two special triangles are, first of all, if we take a triangle that has unit length as both of its legs, so an isosceles right triangle, we get ones and ones, and I guess we might do that journey a little quickly too. And then, so what is the hypotenuse? Using Pythagoras' theorem, we see that 1 squared plus 1 squared is h squared, or h squared is equal to 2, so h is equal to the positive square root of 2. Once I have that, that's how, given any two sides in a right triangle, you can find the third side. So this gives us, I know, exactly, it's extremely useful. Extremely, yes. There are clearly other applications. I'll get to them in other videos. Back off. Just trying to take over the videos now. Once I have that, we can also argue this is 90 degrees and then this is alpha and alpha. Nobody knows their useful properties from Euclidean geometry, but if I have an isosceles triangle, the angles subtending these sides are also equal to each other. And now what I have also is a useful idea, is that the sum of the interior angles in any triangle is 180 degrees, or pi radians. So what we see from this is, if this one is already pi over 2 radians, and the sum of all three of these angles has to be pi over pi radians, we get that alpha plus pi over 2 equals pi radians. So what that says is 2 alpha equals pi minus pi over 2, which is pi over 2 radians, or alpha is equal to pi over 2, which is pi over 4 radians. So long story short, I've derived, I won't do it for the other one, but for this one it's much quicker. So what I've also done is, once we have that, I can now, once I have two unit lengths in a right triangle, I can use the hey, don't mind us, we're just making videos. She felt, oh, she's over here already. I'm scared of her. No, she's embarrassed. That was the cat trying to climb on stuff and just knocked over 6 things. Also why you can't have nice things. Cats ruin everything. Entropy makers, cats, or entropy makers and children. Let me destroy your stuff. Now I know from Pythagoras' theorem, which she did agree with, from Pythagoras' theorem we can find the hypotenuse, and then what she clearly didn't agree with was the fact that I used radians and not degrees to explain this, so she threw a bunch of stuff over in the behind the scenes. So alpha clearly is 45 degrees then, Willa. Be quiet. And we get, this is pi over 4 and pi over 4 or 45 degrees. So once we have that, now I have this nice triangle, which has, that was the long story of, we have a nice unit isosceles right triangle. We have a hypotenuse of square root 2, and then we have the angles. Now what does that give me in trigonometry? The trigonometric ratios now are cos of pi over 4, say, is equal to adjacent over hypotenuse, which is equal to 1 over root 2. And yes, if you want to rationalize the denominator, if you multiply by root 2 over root 2, this becomes root 2 over 2. You're like, isn't that root 2 over 2? Yes, it is. They're the same thing. They're the same thing. Learn how to rationalize. So I like this one because it comes from the special triangle. Sine of pi over 4 is equal to cos of pi over 4. Why? In the triangle, if this is pi over 4, sine of pi over 4 is opposite over hypotenuse. So this is opposite over hypotenuse, which is equal to 1 over root 2. So katoa, I don't memorize these. Oh, now we have to do that too. Just a second. So I don't like mnemonics, but I think everyone's probably, if you're from Canada, you may have seen so ka toa. Have you seen the other one though? Let's do the other one. Cosecant is hypotenuse over opposite. Secant is hypotenuse over adjacent, and cotangent. Choshakao! Choshakao is much better than Sokatoa, so start using Choshakao. Patent pending. Patent pending. Kitty, patent pending. Using these mnemonics, I can get a bunch of nice trigonometric ratios. What we just found out is that cos of pi over 4 is equal to 1 over root 2, which is also equal to sine of pi over 4. Now let's use another special right triangle and we can get all the nice trigonometric unit circle values for sine and cosine in the first quadrant is essentially what this other triangle does. So the other special triangle is now another right triangle. So this one is the 90 degrees. How I always remember this one is cleverly, if you want to remember right now, pi over 3 goes opposite root 3. The 3's are opposite each other. And then this one has to be pi over 6. Also, my brain thinks in radians, so I don't know how you're going to do this in degrees. You're screwed because 30 degrees and 60 degrees. But in radians, pi over 3 is opposite of the root 3, and that's how I always remember the hypotenuse is 2. In here, what do I want from this? I can get 4 more values. What this says is, let's use this one first. This one says sine of pi over 6 is equal to opposite over hypotenuse, which is 1/2. Cos of pi over 6 is equal to adjacent over hypotenuse, which is root 3 over 2. And then using this angle, now if this is the angle, this is the opposite, and this is the adjacent. So what this says is sine of pi over 3 is opposite over hypotenuse, which is root 3 over 2. They interchange their values at this angle. And then cos of pi over 3 is adjacent over hypotenuse, which is 1/2. So these are the magic unit circle values. In the last 30 seconds, let's wrap this up and tie this into what they call the unit circle consistently. From these 2 special triangles, you can memorize these 2 special triangles, which I recommend you doing, and then you have essentially all of the first quadrant unit circle values. So all of these values now on the unit circle, they say if I have a circle, which is the unit circle set at a 0 with radius 1, I start at the point 1, 0, and then after I travel a distance t, I arrive at a point which is sine theta, cos theta. At some of these values, at this value, and at this value, and at this value, we have pi over 6 radians, pi over 4 radians, and pi over 3 radians, or 60 degrees, or 45 degrees, or 30 degrees. Be quiet back there, kiddies. And then this is pi over 2, and this is 0. So in the first quadrant, all of these nice unit circle values, what that now tells us is, essentially, is that we have cosine as the first coordinate. So cos at pi over 6 is root 3 over 2, and sine is 1/2. And then at pi over 4, they're both equal to each other, 1 over root 2 and 1 over root 2. I'm squishing them in there now, but and then at cos of pi over 3, this is equal to cos is 1/2 and root 3 over 2. That's what that unit circle value picture is telling you. It's telling you the sine and cosine values of these exact values of sine and cosine at these angles. We're given 1 trigonometric ratio in a right triangle, and it wants us to find the other 5 trigonometric ratios. So what does this say? Immediately we should draw ourselves a picture. And we have, classically, this is what we can build. So we have an angle, and this is how we get cos of that angle is in a ratio. And what it's telling us is once we fix this, we have cosine theta is adjacent over hypotenuse, which is equal to 12 over 13. So that's telling us this side is 12, then the hypotenuse is 13. And so now we need to find the other side, b or y, depending on what you call it. A squared plus b squared equals c squared. The sum of the square of the legs in a right triangle is equal to the square of the hypotenuse. It sounds way fancier that way, but a squared plus b squared equals c squared. So I can find this third side, b squared plus 12 squared equals 13 squared. So b squared equals 169 minus 144, which is 25. And so b squared is equal to 25, or b is equal to the positive square root of 25. So b is 5. So this is the well-known 5, 12, 13 Pythagorean triple to those who well know it. And we have the third side in our right triangle. So now that I have the third side in this right triangle, basically what we want to do with that is just compute all of the trigonometric ratios. The first three are the definition of them. Sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. And then the other three are the reciprocals of those, or 1/overs. So I can't remember what it is now. The other stupid mnemonic I tried to make up. You'll see. Watch the other video. So I have cosine of theta is 12 over 13. Also, I should point out in some of these, they give them where you're actually in the Cartesian plane and you're in a different quadrant, and it'll say sine is negative. So then what you have to use is combine the information of the ratio they give you and the fact that sine is negative to figure out which quadrant you're in, and then add sines in here. In this one, I'm in the first quadrant, so we don't have to worry about the sign of this. So cosine is 12 over 13, and we have, therefore, sine theta is opposite over hypotenuse, so that will be 5 over 13, and tan theta will be opposite over adjacent, which is 5 over 12. For the other ones, for cos, 1 over cos is secant, so 1 over this will be 13 over 12. Notice that cos is always a number between 0 and 1, and then therefore secant is always larger than 1, and sine will always be a number between -1 and 1. So in this case, if it's positive between 0 and 1, and cosecant of theta will be the reciprocal of this, so 13 over 5, and cotangent of theta is equal to 12 over 5. These are the 6 trigonometric ratios in a right triangle.